Importance sampling is not actually a method for sampling from a probability distribution, as the name might suggest, so it's not sampling. In fact, importance sampling is a variant of Monte Carlo approximation. So it's actually an approximation method. And it's a really cute trick. So I think it's a neat thing to see. Remember that in Monte Carlo approximation, we were approximating the expected value of f of x for some function f and some random variable x by this sample mean, sum as I goes from 1 to n, of f of xi. And here, xi, each of these x1 through xn, was distributed according to the same distribution as x. So x was distributed according to p, and also each of these was. But this was kind of a big assumption here. I mean, assuming that we can actually efficiently draw samples from the true distribution p of this random variable x. So you might wonder, what happens if we can't do that? That certainly can happen. It can certainly come up that we might not be able to draw those samples efficiently. And so is there any way, maybe could we come up with, say, some alternative distribution? Maybe, if we had some q and we could draw samples from q, could we do that and somehow correct for the fact that we were drawing samples from the wrong distribution? And if so, if we can do that, then is it possible that we might even do better? We might even get a better estimator by using a different distribution q than the true sort of distribution of x, p? And in fact, it's maybe a little bit surprising, but in fact, the answer is yes. Yes. So you can correct for that. That may be not so surprising. You can correct. It's very simple to correct for the fact that you're using a different distribution. And maybe the surprising part is that you can do better. In some cases, you could do much, much better than drawing from the true distribution p. And importance sampling is one way to do this. Sort of the most direct way to try to do this. So what is importance sampling? Let's focus on the case of a density, that this p is a density. So this will be for p that's a density. This all generalizes to, say, a PMF or even more general distributions. But let's make things concrete. So this is the thing that we're trying to approximate. And let's write out what it is. It's the integral, when p is a density, integral of f of x, px. And now, let's do something a bit strange. Let's multiply and divide by q of x, so this is this q, for some other distribution q. And we can do this for any PDF q, so q is going to be a PDF here, such that q of x equals 0 implies p of x equals 0. In other words, if there's a point x for which q of x equals 0, then for that x, p of x must be equal to 0. So this will work for any such q. And in the more general setting, I hope this won't confuse you. This is not important, but if you're interested in the generalization, this is what's called absolute continuity. P is absolutely continuous with respect to q. But that's not important. You can forget about that. So, so we can always do this. And now, this, let's think about if we try to do a Monte Carlo approximation, we can view this as some function. This will be our new f, and this is the probability distribution that we're taking the expectation with respect to. So we can approximate this by 1 over n, sum as I goes from 1 to n, of f of xi, p of xi, divided by q of xi, where here I, 1 through n, are drawn according to, maybe put it up here. In this expression, the xi's are drawn according to q. Before they were drawn according to p, but here they're drawn according to q. And this is it. This is the importance sampling trick. It's a very simple trick. Let's write down what the whole thing was. It was that the expected value of f of x, we approximate it by, let's give these things a name actually. Let's call w of little x equal to p of x divided by q of x. So we'll just define this function. So our importance sampling estimator is, it's the sample mean of f of xi times w of xi, where xi is drawn according to q. And these, let's put a box around that. That's important. And this is for q satisfying, for any q satisfying this property right here. And these w's are called, the importance weights, or the importance weight function. This is called the importance weight. These are called the importance weights, these numbers w of xi. And now, so let's think about whether those things I said at the beginning are true. Does this actually correct appropriately for the fact that we're using a different distribution? Well, what happens, so the first thing we would like to say is that this is an unbiased estimator of the mean here. And let's check that that's the case. So if we took the expected value of this, we want to say it's equal to that. So if we take the expected value of this, we get the expected value moves through e of all this stuff. And if we, so this is, these xi's are the only thing that's random here. So we're taking the expected value with respect to q. So we multiply by q of x. You know, this would become an integral. It's just exactly undoing this basically. So this would become an integral of f of x wx times q of x. Then the q cancels in the denominator here. The q cancels with the denominator. And then we're left with the integral f of x p of x. And that's just exactly this. That's just the expected value. So it's just sort of reversing these steps. So in fact, this is a unbiased estimator of the true expectation. So that's nice. And of course, you know, you might actually just immediately see that by the fact that this was a Monte Carlo estimator over here of this. And we know that a Monte Carlo estimator is unbiased, so therefore the expected value of this, which was this, equals this. And so we get all the same sort of guarantees that we have for Monte Carlo. It's unbiased, it's consistent, and you know, it has that expression. It goes like 1 over root n. It converges like 1 over root n. So it has all those sort of guarantees. The variance, though, so the variance will be different. It's going to be the variance of this factor here divided by n. Right, because by the same argument that we used for the Monte Carlo estimator. So the variance of this, let's call this, I don't know, let's call this, this right-hand side, let's give that a name. I don't know, let's call it capital I for importance sampling, importance sampling estimate. So the variance of this thing, the variance is going to be 1 over n times the variance of f of x times wx, which is p of x divided by q of x, just by the same argument as before. So this importance sampling estimate has a different variance than the standard Monte Carlo thing. The standard Monte Carlo thing was 1 over n times the variance of f of x. And this is how you can improve the expected error. You can lower the expected error of your estimator by reducing this variance, because the mean squared error is the bias squared plus the variance if you're using the square loss. So then your expected loss is this, and so your expected error can be, well, it could get worse if you made a bad choice of Q, but if you somehow could make a very smart, very clever choice of Q, then you might be able to reduce, you might be able to make this smaller than this. This could be much smaller than this. And that was the variance of mu hat n, the Monte Carlo estimator. Maybe I should call that IN. And in fact, there's a theoretical optimal Q that you can just, actually it's pretty straightforward, and just solve for the theoretical optimal value of Q. But that might not be, and so it can be much smaller than this. But it turns out that even though in theory, you might be able to write down the formula, it might in practice be very difficult to actually sample from that theoretically optimal Q. So usually what people do, well, oftentimes people will just try to make Q as close to P as possible in order to in the situation, well, so let me say there's two situations, sort of. One situation is where you can't sample from the original P, and so you have to do something different, and importance sampling gives you, that was sort of the answer to the first question, is that it gives you a way to correct for using a different distribution. And if you're just trying to correct for using a different distribution, then you might try to choose Q as close as possible to the original P. The other situation in which importance sampling can be very valuable is if, whether or not you can sample from the true P, you want to improve your estimator. You want to improve upon this Monte Carlo, this basic standard Monte Carlo estimator. And importance sampling gives you a way to do that by what we were just talking about. You might be able to somehow, you might be able to get a Q that will lower this variance. And so you can do even better. Okay, so that's importance sampling. It's very, very simple. You can, I think, just very easily remember how this is derived rather than remember the formula itself. And I'd like to show you in the next video draw some pictures for the intuition of what's going on here in order to try to understand what would make a good choice of Q, and what would really help you to lower your variance, and also how, what would be a bad choice of Q. What situations can arise in which importance sampling can go dreadfully wrong. So we'll look at that next.